Hi, I welcome you all to this session on progressive waves. And taking you along on this journey is Dr. Yunus Jerusha, an assistant professor of physics. We would have frequently come across the terms progressive wave and stationary wave in the science class. Let us look at what they are very briefly. A progressive wave's profile moves forward, which indicates a transfer of energy. Here, energy is transmitted in the form of vibrating particles. In a stationary wave, the wave remains in a constant position due to the interference of two progressive waves of same amplitude, same frequency and same speed, but traveling in opposite directions. They occur by resonance only at the natural frequencies of vibration of the medium. A little bit in detail now. A progressive wave or a traveling wave is the one that allows propagation of energy through the medium as the wave continuously travels in one direction where the amplitude is kept constant. Basically, the molecules in the progressive wave transfer their oscillating energy in the forward direction. This leads to the propagation of energy from one point to another through the medium. Observing the shape of the progressive wave, we have peaks called as crests and valleys called as troughs. Stationary waves, on the other hand, are also known as standing waves. These are waves that possess vertical oscillating movement but do not undergo forward motion in the horizontal direction. It is the result of the superposition of two identical waves of the same amplitude and frequency that are propagating in the opposite direction. Stationary wave generates vibration pattern within the medium, thus energy is confined within it. It never appears to get travelled as the nearby points of the wave are of similar phase, and so the energy is not transferred from one point to another. Observing the pattern of the stationary wave, we have what are called as nodes, where the amplitude of vibration is 0, and antinodes which have a maximum amplitude of vibration. Let us now compare the stationary and progressive waves based on their various properties. The first property we are going to compare is energy and momentum. A stationary wave does not transfer energy and momentum from one point to another, whereas in a progressive wave, energy and momentum are carried forward and they move with the speed c is equal to f lambda, where f stands for the frequency and lambda stands for the wavelength. The next property we are comparing is the amplitude. The amplitude in a stationary wave varies from 0 at the nodes to a maximum at the antinodes, whereas in a progressive wave, the amplitude is a constant for all particles within a wave. The next property to be compared is frequency. All particles in a stationary wave oscillate at the same frequency except those at the nodes. Going on to the progressive wave, all particles will oscillate at the same frequency. Comparing the wavelength for the stationary wave and the progressive wave, it is observed that for a stationary wave, the wavelength is equal to twice the distance between the adjacent nodes. In a progressive wave, the wavelength is equal to the distance between the particles at the same phase. The last property by which we are going to compare the stationary and the progressive wave is the phase difference between two particles. For the case of a stationary wave, between nodes, all particles have the same phase. Any other two particles will have a phase difference equal to m pi, where m stands for the number of nodes between the particles. Moving to the progressive wave, any two particles will have a phase difference equal to 2 pi d by lambda, where d denotes the distance between the two particles. Let us start with the definition for a plane progressive wave. Any wave that moves through or across a medium carrying energy away from its source is called as a plane progressive wave. An example for this wave is a toy duck on the water surface. It is observed that the toy duck moves only up and down, whereas the water wave moves horizontally away from the disturbance of the wave which caused it. Now for the characteristics of progressive waves. The amplitude of vibrations in the medium above the mean position is the same. Energy and momentum are transmitted in the direction of the propagation of the waves without actual transmission of any matter. Changes in pressure and density are same at all points in the medium. The phase of every particle changes from 0 to 2 pi. The progressive wave progresses onward from one particle to another in the medium. All particles have a motion similar to that of its predecessor along the wave propagation, but at a later time. All particles have the same maximum velocity when they pass through the mean position. Particles are momentarily at rest at extreme positions twice during each vibration. If the source is at infinity, a portion of the progressive wavefront will look like a plane, and hence it is called as a plane progressive wave. Transverse progressive waves have crests and troughs, whereas longitudinal waves have compressions and rarefactions. There are two types of plane progressive waves, the longitudinal progressive wave and the transverse progressive wave. Let us see what each of these are in detail in the next few slides. A longitudinal wave undergoes particle displacement which is parallel to the direction of the wave propagation, and the wave vibrates in the direction of propagation. For example, sound waves have this longitudinal wave movement. The next type of a progressive wave is the transverse wave, where the particle displacement is perpendicular to the direction of the wave propagation. And in a transverse wave, the wave vibrates to the right angle of the direction of propagation. This is observed mostly in the case of light waves and whenever there is an earthquake. We now move on to obtain the differential wave equation for a progressive wave. Let us consider a plane progressive simple harmonic wave originating from the origin P and travelling in the positive x direction as shown in the figure. As the wave propagates, each successive particle of the medium is set into simple harmonic motion. If v is the velocity of the particle and y is the displacement of the particle at any time t, then we can write y is equal to a sin omega t, and we all know that omega is equal to 2 pi by t. On substitution of omega as 2 pi by t in y, we have y to be equal to a sin 2 pi by t into t, where small a stands for the maximum displacement of the vibrating particle, or in other words the amplitude. Capital T is the time taken by each particle to complete one oscillation, and small t is the time reckoned from the moment the particle P has zero phase under the influence of the wave. Now, the motion of any particle P prime is exactly similar to that of P in amplitude and in time, but it only lags in phase behind the latter. Let x be the distance of P from P prime. The equation of motion of the particle P prime at a distance x from P at a given instant is represented by y is equal to a sine omega t minus phi, where phi is the phase difference between the two particles P and P prime. If the two particles are separated by a distance lambda, they will have a phase difference of 2 pi. Thus, the phase difference between P and P prime will be 2 pi by lambda into x. On substituting omega to be 2 pi by t and phi to be equal to 2 pi by lambda into x, we obtain a new expression for the displacement y to be a sine 2 pi by t into t minus 2 pi by lambda into x. In the next step, we are going to take 2 pi, which is common for these two terms which are present on the inside of the bracket, out, and we have therefore the displacement small y to be a sine 2 pi t by t minus x by lambda. This we represent as equation 1. In the next step, we are going to take capital T, which is there in the denominator of the expression outside. If we take t outside of this expression, we need to multiply t in the second term present. That's what we've done. Let's see what it is. We have therefore small y to be a sine 2 pi by t in brackets small t minus tx by lambda. We need to make substitutions for t by lambda and 1 by t. Let us see how that is done. We know wave velocity small v is equal to frequency nu into wavelength lambda, and frequency nu can be written as the reciprocal of time. Therefore, v becomes lambda by t. Taking the reciprocal of this expression, we have now 1 by v to be equal to t by lambda. Substituting therefore the obtained terms in equation above, we have small y to be equal to a sine 2 pi nu in brackets t minus x by v. This we call as equation 2. If we have the wave travelling in the opposite direction, then the expression 2 has a small change in sign and it is written as small y is equal to a sine 2 pi nu into t plus x by v. This we call as equation 3. And therefore, equations 1, substitution of 2 pi nu as omega in equation 2 gives us the new expression for the displacement of the vibrating particles in a progressive wave to be y is equal to a sine omega in brackets t minus x by v. This we call as equation 4. Now, in order to obtain the velocity of the vibrating particle in the medium or the velocity of the particle from equation 4, we need to differentiate this. Therefore, on differentiating equation 4 once with respect to time, we have dy by dt to be equal to a omega cos omega in brackets t minus x by v. This we call as equation 5. We differentiate this once again in order to obtain the particle acceleration, and we therefore have d square y by dt square. We now proceed to differentiate equation 4 twice with respect to x. So on differentiating equation 4 once with respect to x, we have dy by dx to be equal to minus a omega by v cos omega in brackets t minus x by v, which is equation 7. Differentiating it again with respect to x, we have d square y by dx square to be minus a omega square by v square sin omega in brackets t minus x by v. But we know a omega square by v square is nothing but 1 by v square d square y by dt square. This we have obtained on comparison with equation 6. And now we have our final expression for the differential wave equation for a progressive wave to be d square y by dt square equals v square d square y by dx square. This is the wave equation for a plane progressive wave travelling with a wave velocity v. Now for some applications of plane progressive waves. It is used as microwaves in microovens. It can be used to generate hydroelectric energy from water waves. It is used in mechanical waves like solid, liquid and gas, and it's useful to many employers working in the music industry, water generators supply, radio stations and other industries where mechanical waves are immensely used. They are also helpful to the geologists to understand the vulnerability of incoming disasters like earthquakes, cyclones or tsunami, so that they can address the people for early precautions. For your break, just have a look at this collage where there are various terms pertaining to progressive waves such as particles, vibrates, transverse, pressure, difference, maximum, position, stationary, useful, harmonic, nodes, radio, clear, medium. So many terms are there. Just have a look at this and while away your time for some time. There are so many references. Some links are given here. You can look at these and increase your knowledge in progressive waves. In this session, we would have acquired some knowledge about progressive waves, stationary waves. We would have come to know what are the distinctive characteristics between plane progressive and stationary waves, and also we have obtained mathematically the differential wave equation for a plane progressive wave. Thank you for your patient listening.